เลยก็ได้ครับกี่โมงแล้วโอเค10 minutes okay so yeah I think yeah people are happy with their homework and I mean even those who were not registered for the class is also welcome to do the homework but yeah, so last week we ended the topic of classical information theory, and then we are getting into the other mathematical foundations of quantum mechanics, which is other than probability theory, which is linear algebra. And so I think yeah, today and tomorrow, so we will have a sort of a makeup class. Essentially, we just move from Thursday to Wednesday just for this week, right? Yeah, I think I'll spend like this lecture and the next maybe on this linear algebra stuff. But yeah, this sort of stuff also in Newson and Chuang chapter 2 or other linear algebra book of linear algebra's book of your for preference. Maybe like Axler linear algebra done right. Yeah. And if you don't like his book, then there's a book called Linear Algebra Done Wrong. The done right thing is because he doesn't like determinant, so he doesn't prove things with using determinants. He just pushed determinant to the like last chapter. But I mean, yeah, determinant is sort of just the area, right? It's kind of like the volume. So if you have a matrix and you can think of it as a collection of columns or rows, and then the determinant of the matrix is like the volume that's spanned by those columns and rows. And so yeah, if you go read the done wrong book, then they just use determinant normally. Okay, so last time we already introduced the Hilbert space, which is in our case, it's a complex inner product space, and the dual space. And the element in here, the ket, would correspond in matrix form. So if you choose some basis to a column vector, this is just a convention. We can, flip the bar and ket around, flip the column to row, but never mind. This would correspond to a row vector algebra. More precisely, we're thinking of elements of the dual space as a linear function that takes in the vector. So basically, this is a linear function that takes in the vector from H and then return a complex number. In particular, if you have an inner product, you can sort of already see this kind of mapping, right? So suppose if we have inner product, which we learned about last time. Say I have an inner product. So usually I write, I'll just put two vectors into the slots, right? But then if I think of this as something that has already taken the one vector as an argument and then is waiting to, ready to take another vector, then this is also a linear function from here, right? And it is linear precisely because this argument here is linear. It wouldn't exactly work if I have a vector in here and then I have a free slot in here instead, because the slot here is like complex linear. It's like Z squared linear. You have to put the star. Right? Yeah, and so I guess maybe for the next few minutes we'll try to make the connection between these two concepts. Okay. Right. So maybe let's do it like this. So if I have a linear functional in H star, and then I'm acting on some vector psi in the bracket notation, this would be just this, right? And we tend to think of it as inner product, but it's technically not an inner product yet. And well, how can we think of it as an inner product? Well, we would be able to do that if we can map this bra to a ket, right? If there is a corresponding ket for every bra. So maybe first, maybe warning, everything that we are doing here is in finite dimension. For infinite dimension, you know, there's some shenanigan happens. For example, the bra, like the position bra. So this is the wave function, right? But then you can think of it, so if I insert the identity, and then, you know, it's like bra x ket bra x ket x prime bra x prime psi, then you know that this is the delta function. So this would be a linear functional. This is a vector. And this is a complex number. You may ask why we are just writing the same thing with an essay. One of them is complex number, one of them is a function. Of course, this is the first, I don't remember whose textbook it is, maybe some math textbook. This is the first fundamental confusion of calculus. That when mathematician, so when I mean vector is the same as a function, right? And I just use the word vector here because we are actually just use all the, we think of it as really sort of like a big column vector, and then I integrate over all the elements. And then here, I mean function of psi at argument x. So to prevent confusion, if you read a math book, then for function they would just write like this without the argument, and then if they put the argument, then they mean the value of the function. But why do I bring this up? Because we know that we cannot quite sort of turn this bra into a ket because because it's not square integrable. Well, mathematically, there's nothing really wrong with not being square integrable, but in quantum mechanics, we would want our wave function to be square integrable. It's like in the L2 space. It's like the L2 space of function, meaning square integrable. Not this guy. So the delta function is not really in this. However, it's a perfectly fine linear functional that you can apply on the function and then get a complex number back. But luckily, in finite dimension, something like this doesn't happen. Okay. As we learn, so maybe one way to see it is that one way to think about it is that the dimension of H and H star in finite dimension is the same. And so you cannot have something more than sort of like more than the original vector space. in the infinite dimension case, yeah, when you take the star, you actually get something more. But is the statement that the dimension of the two are the same is still true because both are infinite. Yeah. So this is just something that we don't really have to think about, luckily. Uh, yeah, so we given an inner product. So usually we just take the standard inner product, right? But you don't have to, right? So it's important that given an inner product, you can identify a brand, a kit, with respect to that inner product. We can make a correspondence, give a correspondent. So between the bracket and the inner product, in the following way. So recall that last time we talked about the dual basis, so the basis of linear functional in H star, right? And there we define it to be like this. So the basis Fj, when when it acts on a vector, basis vector Ek, then I say that this is just a Kronecker delta. And so it's sort of clear by this that if I choose this basis, sorry, I think it's clear that if we want to interpret this as an inner product, then I basically would take this to, if I map to H, from H star to H, then this should be the basis. So I mean, we might as well just write it like this. And then for a general vector now, we just make this rule. So if this. So if I have, so if this is sum over, okay, I can write either way first. Maybe it's more familiar to just do this. So yeah. So then given a fixed basis, right? If I write a vector like this, like I write a kit right like this, and then we say that it's corresponding to this. Right. Yeah. Again, it's kind of important to emphasize that the action of taking a complex conjugation of a vector is basis dependent. For example, you could why is basis dependent? Maybe the easiest way to do this, to see this, that you can always define a new basis that absorb, say, any complex phase in here, right? And then if you do that, then in this new basis, complex conjugation would be different. You would get a different vector. Well, and why do we have to take the complex conjugate of the elements? Can you see why from the property of inner product? Sandwich between what and what? well, that doesn't really work, right? Because this is still the same no matter what. It doesn't it doesn't know. Well, if you already choose this basis, choose this EJ as a basis, and there's no coefficient. So in general, you can take the bracket of any pair of vector, right? But if I take the bracket of the same thing, so then in this basis, well, so I guess let's just define right here that this is called orthonormal basis, right? If it's normalized orthogonal and it is also a complete set in the sense that it spans the whole vector space, and then you also have this property which we'll come back later. It's kind of a projection operator. But here in the orthonormal basis, well, what is this guy? Yeah, so let's just do it, right? So if the expansion coefficient of this is just some c, and then here if I use this rho, I put the complex conjugate here, right? And then this turn into a Kronecker delta, so we get rid of one of the sum. And then this would be what we already know. And then in general, so let's say if this is d j sum over dj ej, in an orthogonal basis, this would be CD, right? But now you can see that if we if there's no complex conjugation here, then this is not guaranteed to be positive. Okay. But by the axiom of the inner product, the inner product of a vector with itself must be positive, and it must be zero only when the vector itself is a zero vector. Right? And so the complex conjugation is just there to prevent, to make this actually an inner product. All right. Before we move on, want to show something real quick. This is pretty useful inequality. Called Cauchy-Schwarz inequality, and the way I remember it is that this says that you can bound the inner product by, you can, okay, what I said was also correct, but I would say you can bound the inner product by the norm, by the length of the vector. And this is why, for example, like in quantum 101, we would first say that, in the physical Hilbert space, we want the vector to be normalizable, right? So we want this to be finite, but that automatically means that every inner product of a pair of vectors in this space is also finite. Then this is useful for a lot of things. Quantum computing, like in query complexity, or when you want to bound the error of like each contribution of steps of computation, or in like quantum metrology when you use the quantum principle to design better measurement. For example, you have you can prove something like the quantum Cramer bound using this. And if you haven't heard of the Cramer bound, it's just about it's related to the surprisal or information a little bit, but it's about on the variance of any possible estimator for the value that you want to estimate in a measurement. Okay, so how do we prove this? Have you seen a proof of Cauchy-Schwarz inequality before? Do you remember the proof? No. Yeah, I have to remember it too. So there's probably. Yes. Yeah. This is one way that I remember, just to remember it somehow come from the Pythagorean theorem. Yeah, and that's the way that I'm gonna do it here. So let's say I pick. Yeah, we are trying to use Pythagorean theorem, right? So this is let's say I try to split this vector into the part that is parallel to phi, although I don't really want this to be phi. I want this to be just the unit vector as a coordinate x, one of the coordinate axes, which is right. So if I want to really divide by the norm, so maybe it's this guy. Well, we'll see either way. And then, okay. Then I call this the orthogonal part. This kind of this constant is kind of get in the way. So this, and then this is the parallel part. And I'm gonna do, let's say this is A, this is B, this is C. So of course, Pythagorean say that this is true. And then we now spell it out. Right. So it's important to remember that the norm of the vector is actually this and not the right. So we have a square there, so like a 2 norm instead. So yeah, the square root here means that the square root there means that I don't really have to take the square of these guys. Okay, so what is this? So this is in the direction of phi, but then you project it, right? So basically you act on it with the projector here and then normalize it. But of course, for convenience, I just switch the order of this. Oh, sorry. All right. Yeah. Sorry. Yeah. So you project psi onto phi, right? And then normalize it. So right. So the normalization is just yeah, it's just this, like by the square. And so it means that the inner product of this guy is this. But then the normalized for the denominator, you get a square of this, and so it cancel with the guy above. Right. And then you can sort of already see how it will go, right? Because we want an inequality here. If I throw this term away, which is always positive, I get the less than or equal sign here, and then I just move this guy to the right. And we got the Cauchy-Schwarz inequality. Now, of course, the $1,000,000 question again is, when is this inequality saturated? Right. Do you want to answer it? When does this become an equal sign? Well, no, right? Because if this is 0, but this is never 0 unless it's a 0 vector. There's 0 vector. Where you look at the way that we do things here, right? So I just throw away this term, and so that means this has to be 0 for the equal. Yeah. And so to put it inward, so the inequality, Cauchy-Schwarz inequality is saturated if and only if phi is already parallel to phi. So if it's in the same direction already, same direction or opposite directions, and parallel or anti-parallel. Okay. Saturated when this is a scalar multiple of the other vector. Okay. Any questions so far about inner product and bra and kids? Norm. So here we, well, I erased it, but here we define a norm using inner product. And you can always do this, but the other way around is not true. There's some norm, for example, the max norm. If you just take the max value of the vector, and that cannot be turned into an inner product between two vectors. Right. What's next? So we already see there, right, that this guy acts as a linear operator, right? Because when you put it against a ket, then you got a bracket which the bracket turns into a complex number, and then the complex number just commutes with the vector, so you can just put it anywhere, so the end result is just a vector. In particular, this guy is a projection operator. Right, as you can see, the like geometrical interpretation there. It just gets rid of when I project it onto psi, it just get rid of the component that are orthogonal to psi. And we'll come back to this later, because there you can to characterize projection operator, you will need the adjoint. So next we're gonna talk about linear operators. So of course, everyone knows why it's called linear. This is the definition, right? So whenever it acts on a linear combination of vectors, you can always act on each term in the linear combination separately, and that's why to define action of a linear operator on the whole space is sufficient to just define its action on some basis. We can so let's see. So if I have an O and B again, well, let's see. Maybe I want to be a bit more general. So if I have a basis, and I will, let's see, I will put an overlay here, a bar here, just to remind ourselves that, I mean, it doesn't have to be orthogonal or normalized. Then if I act on one of the basis element, so usually I would just get a linear combination of them, right? And this is just follow from the usual matrix multiplication. I write it in the weird order just because then I can have J adjacent to each other. And this is saying that the matrix form of this, so if I write it in the matrix form, so let's say if the dimension is small d, sorry, is that this is a row, this is a column, this is the row. Okay. Yeah. ADD. So this is saying that if, say, I put in the first basis vector, I would get the first column. So I think I find this way to be sort of, if you remember, this is kind of convenient to use, just that the column, each column of the matrix here is just the output when you when a basis vector is an input. Yeah, so for example, this is A of E1. But how to write this in bracket? Well, the way that we are familiar with, you really need to use the orthonormal properties. So only in O and B, because we want to use this property. So I put the bar out, right? Because this is already assumed to be O and B and O and B. So if I can expand, right? On both sides. And then call this the matrix element. Because this is precisely what I would get, right, if I act on the right by the basis vector ek. Right? On the other hand, if say if the basis is not O and B, is true. I think yeah, it's true that I can still write this. However, I cannot single out like I cannot get one element, one matrix element out just by acting on by the like the EJ bar, right? Because it's not gonna be orthogonal anymore. Yeah. So this is the same deal with the trace. For example, if you calculate the trace, and the basis you choose is not orthogonal, then it's not true anymore. That the trace is a sum of the diagonal of this. Yeah. So just be careful. It's just something that has to do with Dirac notation. Right, right. So I think that would be a good point to talk about the trace now. Right. Yeah, if you have any question, you feel free to ask anytime. Well, so I can give two equivalent definitions. One is that, well, maybe the usual one is that the trace of a matrix is the sum of its diagonal elements. And this definition is immediate to see that this is a linear function. Another one might be the one that you see less, but is pretty useful. Is that the trace turn an outer product into an inner product. And the nice thing about this is that it's clearly basis independent. Have you seen the second definition before? Yeah, it's right. And now we can try to think about why it would be equivalent. Right. So which way and can go first? Well, it doesn't matter, I guess. So if I assume this, and then I assume let's see, how do I want to go? Mm-hmm. Right. So trace A. Okay. So I want to show the second definition using the first, right? So if I have, we can do this by assuming O and B and then write this. So if I have an O and B, then according to the first definition, it would just be the sum of the sandwich. But now these two are just scalar, and the psi and phi doesn't depend on j, so I can swap them and then pull the summation inside. So the phi ej psi. But then since it's orthonormal basis, this is just the identity. Right? And so that's the first definition. Or you can also prove directly from the first definition that is basis independent. So maybe I just put a little note here. The basis independence of the first definition. Right. So assuming an O and B again. So if I have it in one basis, right? But then now I want to use a different basis. So let's say it's Fk right. And now if I swap the sum again, let's see, I just leave a space here because maybe I just want to put a sum in later. Okay, I can do that. So this is sum over k and this is sum over j. And then again, this is the identity, and so we see that we can change to any orthonormal basis. Do this. Yeah. Yeah, and you can think about why writing like this would be wrong if the bases are not orthonormal. Even though generally you can calculate the trace in any basis, right? It doesn't have to be normalized or orthogonal. But clearly, if in this way that we are usually writing matrix elements using Dirac notation, it's clear, right, that if I scale the basis vector, then this quantity would be different. So that's sort of the, yeah. If you really want to write the trace, if you have a basis that's not orthonormal and you want to write a trace like this, then if I pick a basis here, I have to pick a dual basis here. Yeah, but usually in like in quantum information, that's almost everybody does. You just pick an orthonormal basis. But say, for example, an quite famous non-orthonormal basis, where usually is in the infinite dimensions, they will have something like coherent state. I don't know if you have seen something like coherent state. Okay, maybe it's a long story, but yeah. Yeah, I mean, even if I write in terms of linear combination of the number set, it would like not be obvious. But it's basically a set of, so people say it's the eigenvector of the annihilation operator. And it is a complete set. It is a complete set, but maybe it's more accurate. The people say that it's an over complete set because it's a, well, okay, it's an infinite set because you're in an infinite dimensional Hilbert space, but it turns out that it's actually more than that you need for the basis. And moreover, they are also not orthogonal. But since it's complete or over complete, you can expand any operator or any state in that coherent state basis. And but if you do that, then yeah, you have to be careful about like what the formula that you might be familiar with, like remember, might not work. All right. Now I can do, I guess, just from definition 2 to 1. Now I want to show that is the sum. Yeah, maybe I want to show that it's linear first. And this is what I just thought up quickly. Maybe it be satisfactory or not. But for example, I can, so I guess this is a sketch. So if I put some linear combination of vector in here, then by the definition, the second definition of the trace, it must be the inner product of this linear combination and that guy, right? Which then, if I use the linearity of the inner product, it would just be yeah, and this would, this would force when I split it like this, yeah, this would force the trace function in this definition to be linear as well. But usually I think we'll just say that, okay, you just extend this definition by linearity. And now if you do that, then this thing, when I write it in orthonormal basis, is linear, so I can pull the sum outside, and this is also scalar, just a scalar. And then I apply the second definition, which will just be a Kronecker delta, and then you just collapse the sum to just, sorry, JK. Right, has to be right here. Just, and this Kronecker delta collapse the sum to just one sum. Any question? Yeah, so the trace is a function from the Hilbert space, or okay, it's a function from the operator space to a complex number, and it's linear, it's basis independent. Another useful property to note is the cyclicity of the trace, or maybe this is not so usual word, it's like cyclic property. Which is to say that if I have some operator, then I can permute them cyclically, and the trace would still be the same. A, B, C. So clearly it means that if I have a product of two matrices in here, then I can switch the order. But it's yeah, it's just not true that if I have more than two products, then I can switch it to any order. It has to be a cyclic order. Maybe at this point, it's nice to define the commutator as well, which, I mean, everybody already knows. Just the difference of the product in a different order, right? And then the interesting thing is that because of the cyclic property of trace, if I put a commutator in a trace, it's always 0. So now I can leave you with an afterthought that if I write the commutator of the position and momentum operator, what is happening here, but yeah, I just leave that as for you to think about. Has anyone ever asked Salvatore this question? I think he will love it. Because he would just, I'm sure he would just go on into like domains of operators and like his favorite topic. Okay, right. Half an hour left. Okay, so we're coming to something as a preparation for something important, the adjoint of an operator. So this is defined in regard to define using it in the product. Right? So I'm gonna write this without not using the direct notation first, because I think it's a bit clearer that way. So usually it is is defined implicitly through inner product. That is to say, if I have an inner product of two vector and then I have an operator acting on this side, then the adjoint is defined this way, that it is whatever the operator that act on the other side of the inner product and then give the same thing. You can sort of already see why it's kind of cumbersome to write in a direct notation, because direct notation doesn't it doesn't distinguish between acting on the right and on the left. So if sometimes I like to abuse notation, and I would write, if I want to do this, there is a better way, but this way is sort of most of the time just good enough for me. I would just put the operator in the, even though you understand it's an abuse of notation, right? Because the symbol in the cat and bra is just supposed to be just the label and not the vector itself that you can like act on. But so if I want to write this, not to confuse myself, just let's see if I have it in my note. No, so let's just figure this out now. So if I want to write this, I mean, one way to write it, I guess, is this, which is a bit of the opposite way. Or I mean, if you want this to be consistent with the other line, I can just swap the two. Yeah, so in this convention, you're sort of thinking of operator as acting on the right, even though it can act both way, right? But then it's just say, if this is just saying that, okay, if I have a dagger acting on psi, and now I want to switch to some operator acting on sorry, a dagger, did I say it correctly? A dagger acting on phi, and if I want some operator to act on psi, then I flip it using the complex symmetry of the inner product. And so I just put this here, and then this is called A, but we can show it formally, but you know that it doesn't matter which way I put it, right? But yeah, let's show that. But okay, first, let's just list some properties. Of the adjoint. And I don't think I'm gonna prove all of this, but I just want to say that it can be proved directly using this definition inside the inner product. Right? So some properties. This is complex. Trying to use the same terminology as the as when we introduce the inner products. So if I take an adjoint of a linear combination, then the complex scalar comes out, but it's become a complex conjugate. Yeah, and you can prove this, for example, as a sketch. So you can put the linear combination of operator on this side, right? And then now if I want to, either you can flip it to the other side and use the linearity, or just do it on this side and use the complex linearity of the inner product. Second, right, the matrix element of this is just the complex conjugate transpose. So which means in an ONB, here I'm just translating it to direct notation. In particular, this also means that if I take the dagger twice, I just get the same thing. Well, maybe let's say 2.5, because it's actually the same. That if I have an outer product and I take the dagger, then it's just switch the two in the outer product. And you can sort of see that it's the same because when I expand operator A in the basis in an outer product, right? For this to be true, then it means that right, in particular, that if I have this, if I expand A as a linear combination of this, and then I have to take the dagger of this, it must be true. That you have to switch the order here, right? The another sort of abuse of notation here that some author will write. I don't remember if Sakurai also write this, that or maybe someone else, that if which actually it doesn't really mean anything, because adjoint is defined only for an operator. But it's well, if this is true, then at least this is also true, right? Because you can switch order and then flip bra in the kit. But it's sort of true in a matrix form, just because that this is a column vector, and this is and then you imagine that applying this, and then say, oh, it's just, I just transpose it and then take the complex conjugate of everything. Yeah. Yeah, I think I see it somewhere before. And the third one is that if I take dagger, we already had linear combination right now. If I have a product, then sorry, I just switch the order and then take the dagger of each operator in the product. And again, you can show this as well using just the definition of inner product. Basically, you write something like this, right? And then I can switch this guy to this side, and then now I can split this and like distributing A and B to the other side one at a time. Yeah. Okay, so that's the sketch. All right. Now that we have the notion of an adjoint, we can start talking about the part of linear algebra that is the meat, the what is relevant to quantum mechanics, right? Which is something like Hermitian operator, unitary operators. But maybe you start with something simple first. So a projection operator. So we already see that if I have an outer product of any vector, some vector, it is a projection operator onto that vector, right? So in other words, it's a projection onto a one-dimensional subspace. So now if I start for any, so let's say I have subspace S. And then if I choose a basis such that orthonormal basis that span S, and then sum over, this is a projector onto that subspace, right? In particular, is also an identity operator on the subspace. Yeah, so the picture is kind of like this, right? If I have Hilbert space here, so let's put this outside somewhere. I have some part that this projection operator, so outside, so suppose is S, so it will just project out everything orthogonal to S, right? Usually I just say that this is the kernel of the projector, and sometimes I just say that this is the support. So in here it just means because the projection operator can always be diagonalized, right? Since it's clearly just the identity on the subspace itself, the support just means the eigenspace where the sum of eigenspace whose eigenvalue are not zero. Okay. But here especially it's just eigenvalue 1. So in general, the characterization of projector is that, so let's say P is the projection operator if satisfy both of the following. The P itself is Hermitian and P square is the same thing. So I think the second property is clear, right? That what they mean is just if I projecting a vector onto some subspace and then keep projecting it, nothing is gonna change, right? Because I already get rid of the part orthogonal to the subspace, and then the it acts as the identity on the subspace itself. What might not be so obvious is the first, and this is just to prevent. So there are, for example, some counterexample of operator that satisfy the second property but not the first one, and it is not a projector. For example, one that I remember from the top of my head is something like this, and you can check if this is true or not. But the what is wrong with this? So basically, it maps both basis element to the same subspace, right? So it's sort of it sort of leaves the some subspace alone, but it doesn't get rid of the orthogonal, the vector component in the orthogonal subspace. And so now we know that, okay, so if property 1 is true, then I can also, this mean is also Hermitian, right? That I can diagonalize it and it has all real eigenvalues. So by diagonalize it, I mean that we can choose its eigenvectors to form a complete set of the vector space, right? Yeah, complete orthonormal set, or complete orthogonal, and then if you just want the normal part, then you just normalize each one. And once you normalize it, once you diagonalize it, you can see that the second property just means that the eigenvalue can only be 1 or 0. This is the idempotence is just something that is really just a word for this, something that's square to itself, but for real number, for number it's just 1 or 0. All right. A little question. So now if I have something like 2 subspace, if I multiply the projector onto the 2 subspace together, so what do I get on this side? Is it still a projector? Yeah, I can have my coffee break. It must be a projector, or it's right.
Yes, something like we 3D on some 2D plane, right? And then we project on some
Yeah, if you project on some 2D plane and then another projector on another 2D plane, which is not the same, then you will get the line that intersect them. Right? So this is a projector onto the intersection here. Maybe another way to see it is that since it's the identity on like this guy is the identity on this subspace and the other guy is the identity on the other one, right? So so clearly, so things that are not in the intersection would be projected out by either of them, but the stuff in the intersection, the product of the projector would just act as the identity, of like identity times identity. Yeah. Yeah, this was one of the homework from Kohen Tanuchi, right? From last year. Yeah. Okay. And right, and if you recall, one of the first lectures, you will see that this is consistent with when we think of the logical operation and or, and then I think of those as like projection operators. Yeah. Because earlier we would say that if I have proposition S and S prime, and then I put it, I juxtaposition them like this, it's sort of by definition, it was a definition of the intersection, sort of like, yeah. And then I mentioned that the algebra of projection operators also follows the Boolean algebra. All right. do I need to say that they commute also? Yeah, because in the Boolean algebra case, I would just restrict to like all the projectors that commute with each other. Yeah. Maybe. Projector. So what are operators, other operators that can be diagonalized? So we just talk about Hermitian. Then any other classes of operators that you know? Yeah. And what are its eigenvalues? It can be any phase, right? Yeah. So maybe just make a note about Hermitian operator here. So the spectral theorem for Hermitian operators. So this is, of course, an operator that is invariant under the dagger. The spectral theorems state that any Hermitian operator or one can find, let's say like this. The set of eigenvectors of Hermitian operator can always be chosen to be a complete autonomous set. Can always be chosen to be complete and autonomous set. Of course, we know what eigenvectors are. So if I denote the j eigenvector of A just by little aj, then this would just give this is just the eigenvalue equation, right? So I just use the Sakurai notion and just use the same label for eigenvalue and eigenvector. And this here just means that I can choose this set of aj to be an O and B. And furthermore, the eigenvalues are real. Value be real. So in particular, when since it's diagonalizable, I can always write an operator and Hermitian operator A in this form, right? Where this is real, and this sort of the manifestation of the spectral theorem in in the Dirac bracket notation way. Just some terminology, I would say that there are degeneracy if different eigenvalues here are the same. If there's the same when j is not equal to k, so like they project onto a different one-dimensional subspace, but the eigenvalues are the same. So I can collect the eigenvectors with the same eigenvalues into one projector. And what I mean is this. So let's have two labels for the eigenvector, and maybe the j just labels non-degenerate eigenvalues. And then the alpha is just a degeneracy count. Then I can, let's say, if I write a projector onto an eigenspace with eigenvalue aj, then I can write in this way. And so it would be, a lot of time it would also be convenient to use this and then write the operator A as a sum of projector weighted by the eigenvalue. For example, when you think of a Hermitian operator as a measurement, right, the way that you would calculate the post-measurement state is that you project the state that you have using an operator for the value. So if you measure and then get an outcome j, then you use the projector pj to project your state. And then the probability is also calculated from pj. You just sandwich pj with the state psi on left and right. We'll come back to this later when we talk about the axioms of quantum mechanics. But yeah, when we talk about the axiom, it's gonna be very brief because we sort of already assume that you have, you already used to non-relativistic quantum mechanics. Okay. Since we were 10 minutes late, can I have more like 5 minutes? Okay, thank you. Right, so that's about Hermitian operator. Another kind that are diagonalizable is the unitary one, right? So, and the definition is this. These are operators whose inverse its dagger, right? And it has to be both the left and right inverse. But for finite dimension, either way would also imply the other way. And so you don't have to, you just have to prove one thing. This is not true in infinite dimension. For example, you can look at an infinite, infinitely long vector, and then think of the right, I don't know which direction you think of the vector pointing, maybe shift the map that shift down and shift up. And it turns out that they are dagger of one another, but since the shift up map, so the shift up map would just destroy it, would just kill the first element, right? So it doesn't have an inverse, for example. But in finite dimension, you can do something like this. Okay, so let's quickly prove it. So if I assume this, and then I want to see if this is true, right? So if I yeah, maybe move it a little bit to this side because it's probably long. Let's see. So I want to so let's see, what is this? So that there may be many proof, right? But let's consider the square of this guy. So now when I expand it like this, then from the assumption I know that this is the identity, right? So and so it's square to the same thing, and therefore it must be a projector. Okay. So so let us define this to be the projector. So how do we know that is the identity? It doesn't do anything, right? Because if I take the dagger again, right, then I switch the order of this guy, and then I take the dagger, and so it's the same thing, yeah. Which has to be true, right? Because it's a projector, it must better be Hermitian. And this is it's kind of obvious, but I think it's a useful thing to know is that you can find the dimension that the projector is projected onto by taking the trace of the projector, right? Because it's basically the identity operator on the subspace, and then it has, so the eigenvalue is just 1 in the subspace and 0 otherwise. So if you take the trace, it will just count the number of 1, right? So then trace this, well, but inside the trace we are free to switch the 2, and we already assume that this is true. Trace. Yeah, so this is just this line does not say that UU dagger is the identity yet, but the dimension implies that it must be the identity, and so it's if this is true, then this is also true. Right. Okay, I just write down a few equivalent characterization of a unitary operator. One is that it's preserved in a product. And all of this should be easy to verify, right? Or you have already seen it. Equivalently, it takes an orthonormal basis to another orthonormal basis, right? Because it's preserved in the product. In particular, it's preserved length of the vector. And 3 is that if you look at the matrix and want to see whether it's unitary or not, well, you can try to do this, but another way is that the row and columns are orthonormal basis as well. So for example, if you look at the columns, then each column is each column, when you think of it as a vector, then it must be normalized and also orthonormal with like other vectors as well. Okay, right. So I haven't talked about the diagonalization of this yet, but next time we'll actually talk about the real version of the spectral theorem for us, which would be that normal operator has a complete orthonormal set of eigenvectors as well, and these are the guy who's that commutes with its own dagger. Yeah, and you can see that this this fits this generalizes the definition of both Hermitian and unitary metrics as well. Okay, thank you. Yeah, for those who come here.